All right, so let's just start this. Today, I'm going to talk about efficient conversion probability estimator for display advertising. For the ones who knows about display advertising, you know what I'm talking about. But before talking about the statistical aspect of it, I'm going to just give you a very brief introduction about display advertising first, and then I will talk about the stat part. But before I start talking about that, I'm going to just say this is a joint work with Dr. Altman, my PhD supervisor, and then also Tom Loggin, another professor at SFU. Those are just like both of them are great people, and then I learned a lot from them. Okay, so let's just start from display advertising. Just to kind of like briefly talk about what display advertising is first, and then talk about the issues and the challenges coming from that area. So if you noticed that before, when you, for example, that's just an example, when you Google something, it doesn't matter what, especially when you're looking for something to buy, or you're looking for some sort of like sales somewhere. So when you just punch in your keywords, and then you get your search result page. If you look a little bit more carefully, you will see in the top a couple of items. There is a little tag with the name ad just right on the left side. You can see it in the picture. So if I just 1 sec, if I can just maybe, oh, what is this? Yeah, I know that. Oh, okay. So let's see. So what I want to do, I'm going to just make sure I can annotate so I can add more stuff into my slide. All right, this is better. So if you just look carefully, you'll see there is this little tag of ad. It seems I can't really do that, unfortunately. It doesn't like it.
I think that's because it's an image, Abdullah. Maybe in other area you can write, but that's
it shouldn't be a problem because it's just annotated right on top of like everything. Doesn't matter it's image or anything else. So let's try it one more time and then see if it works this time. No, it doesn't seem I can. Okay, so apparently when I go for full screen, I can't really do that. It's okay. I'll try just to talk over it instead of like actually writing anything on it. So if you see there's a little tag, it says ad right next to the like on the left side of your result. Those are not actually the search results of your keywords. Those are instead some ads that Google decided to pick and then display it to you. So they are definitely related to what you're looking for, but they are not exactly based on the algorithm Google uses to kind of like look for stuff like pages, web pages to show it to you. And then you can see something similar at the very bottom of the page too. So those are the items that Google displayed to you and making money out of it too, like a lot of money. So that's one of the examples of display advertising. And then obviously, if you click on that, you will be directed to the advertiser web page, and then you probably will be asked to kind of like purchase something or subscribe to something or something similar. So that's one example of like display advertising. I wanted to show that to you, so you have a better sense of what I'm talking about. Of course, if you Google machine learning at this point right now at this age, because this screenshot is just a couple of years old. So if you do that now, you won't see that because there's like tons of different materials on machine learning online for free. So there's like no point to kind of like show you advertisement. So let me move on. So how it works. So when Google shows you those ads, basically, like those ads could be anything. It could be like text, images, videos, interactive videos, and then anything similar to that. And it doesn't have to be in Google page. It could be like an application, mobile application, in other like web pages, in some other applications. Like let's say you're doing like some video games. You always see like some spots in different spot in your phone screen or on the page that you're looking at. So those are all examples of display advertising. So they create those ads and then they place it to the websites, to their web pages that are relevant to what you are looking for, and then relevant also to what the advertisement is trying to sell. whatever that is. It could be a product, it could be kind of some services or whatever else. And then so once they like a connection like Google finds a user and then an ad that are kind of like relevant to each other, and then Google thinks that's a good match, then they will just show the ad to you as a user, and then you will be if you got interested, you will just click on it for display advertising. What usually happens next is just you click on it, and then you will be directed to the advertiser's web page. So that's the process. It happens every time that that you kind of like encounter with the display advertisement. Of course, they created those ads like beforehand. That's not on the spot. Okay. So now we know what display advertising is, and then now let's just talk about like the prices and then the cost. How they come up with the kind of like the way to calculate the cost for the advertiser. So now let's say I'm an advertiser. I have a company, and then I want to kind of advertise my products, my services. So there are usually, I mean, there are like tons of different ways to do it, but like the main three categories of like kind of calculating the price and then the cost comes with this display advertisement is like these three. So the first one is cost per mile, or CPM, and then how it works is just like I'm gonna from now on I'm gonna just say Google, because like everyone knows Google, but it could be basically any other company that does display advertising for companies. So it could be anything, any third party. But from now on I'm gonna just use Google because it's just easier, and then it's more well known. Like everybody knows that. I'm not promoting Google. I'm not working for Google. That's just an example. Sorry for that. So CPM, how it works is just basically for every time that, like, let's say Google display my ad, I need to pay for it, and then every display basically called an impression, and then usually it's just called per 1,000 impressions because there are going to be tons of that, right? Just to kind of like make it more scalable. So they would say just per 1,000 like impression. That's another example. So I need, as an advertiser, I need to pay for every single display of my ad, no matter if like the user got interested or not. So this is not, you can see this is not the best way of like advertising, promoting some sort of like product. So there's another way that would be kind of like more promising. And then how it works is, I would, as an advertiser, I would say I'm not going to pay for the displaying ad. I will pay only if the user clicks on my ad. So just like showing and then displaying my ad would not benefit me. So I will be waiting till somebody clicks on my ad, and then that's the time Google can charge me. So that's going to be kind of like more targeting, because I'm going to just pay for the people who actually click on the ad. So that means Google needs to be kind of extra careful to see who the ad Google is going to show to. So that's a kind of like more important, right? But somebody like, let's say me, like I'm kind of more picky, and then say that's even not enough. Like let's say like many people click on my ad because it's just like so fancy and so interesting, because just kind of like catch all the eyes, and then people click on it. But what will happen next? Just nothing. Maybe they won't purchase, because like after clicking on the ad, they will be directed to my website as the advertiser. So now in that website, I will be waiting for the users who clicked on the ad to kind of like do something extra. Let's say purchase a product, or subscribe to some sort of plans that we have already in the website, or anything, any other actions like that. So I may argue, okay, so I won't get anything out of that ad until like the users do that action, take an action, and then let's say purchase something. So that would be another thing. Then Google's would not be able to charge me until the user actually take that action. So the last one called like CPA, cost per action. So you see that like there are three main different ways of like calculating the cost for the advertisement based on what exactly they are looking for. So during this talk, I'll focus on CPA because that's a kind of like more challenging question to answer. But there are interesting questions and the problems in the other two. But for all of them, you'll see some objective function like the one that I'm showing right here to you. So basically, expected price per impression. So we want to know, like, no matter which approach we use, we still want to know, like, how much will cost, let's say, how much would cost to display an ad for every impression, basically. So how it works? We say, like, we first of all, we call this expected value eCPM, and then it would be equals to the cost of that action, CPA, times the rest of it is just basically Bayes theorem. Probability of conversion given click times probability of click, because we know CPA only works for the ones who click on that, and then also they take that action. And then, by the way, like, that conversion, I will define it more formally, just in a minute. But conversion means basically whenever the user takes that action. So when they take the action, we call those users converted, and then we call that event conversion. So CPA only works for the ones who clicked and then also converted. So we have that, like, joint probability of click and the conversion, and then for simplicity we use Bayes theorem to kind of separate those two probabilities. So we get probability of click times probability of conversion given click. All right, so now CPA is some predefined cost per action. So that's something like Google needs to decide, of course, by discussing it with the advertisers. But there are two probabilities that Google needs to estimate. The first one is probability of click, which is a kind of like relatively easier question to answer. It's an easier parameter to estimate. You will find out why that is easier. And then the second part, or the second probability that we need to estimate, is probability of conversion given click. Which is kind of like the main challenge or the main stake here that we need to answer to. So that is just, let's say, basically the very last quantity, probability of conversion given click, means we only will look at the users who clicked on the ad. So kind of like ignore everybody else. And then you will see like what is the proportion of those users who will convert, or who will take that action, or who will purchase the product. So that's the quantity we are trying here to estimate. All right. So let's define different terms that I just used. So the main question is, what is the conversion probability? And then we are still like talking about cost rate, like CPA. And then conversion probability, as I said it before, is just a proportion of users who take that predefined action on the advertiser's website. Let's say purchase a product, purchase a good, and then this, like, what would be the solution? Because okay, so now you know the outcome that we are interested in is a binary outcome, whether the user who clicked on the ad will convert or not. So that's a kind of like binary outcome. So we like, if as a statistician, if somebody asked me that question, I would right away say probably logistic regression would be kind of like a simple and then promising way to answer that question. You got a binary outcome, and then you want to estimate probability of the ones that get converted, like probability of y equals to 1, let's say. So that would be logistic. It's a classic question in stat, and then everyone knows logistic regression is simple, it's fast, and it's not bad, like in terms of like accuracy. But the issue is there is another issue that I haven't talked about it yet. There is a delay between the time that user click on the ad and then the time they would take that action, let's say purchase that product. And we don't know how long this delay would be. Interestingly, it could take hours, days, even months. I remember with a company that I was talking to, they would track the user for the ones that kind of click on the ad for 3 months to see if they would take that action or not. So that's not a short period of like, it's not a matter of a couple of minutes or even hours. It could take like days and months. So you see how complicated this could get, because you can look at your users, you can look at the ones who click on the ads. So I'm going to just call them just clicks from now on. So you can just look at your clicks and then see, okay, so some of them got converted and then some of them not, or most of them not. So are they still going to convert at some point in future or not? We don't know that. And then that is the main challenge here. So we can't really simply go and then use logistic regression. Or I mean, we can, of course, but that's not going to be a good solution because we are going to ignore everybody who is going to convert later in future. We just haven't gotten in that point in time, but we might or we will. All right, so that's hopefully this is clear so far. What the question is, what the problem is, what the challenge is, what the challenge is, and then now let's talk about like different solutions that we can do, or we can kind of like approach to tackle this question. Okay, so this is just another plot that just show you like what different types of users we may have in the data set. So these are all clicks. So I'm talking about like from now, I'm only talking about like the ones that are like who click on that, not the ones that just look at that. So for example, user A is the one, like a user that click on the ad but never converted. Okay, so maybe I have to clarify here. We need to define a window that we will follow the user. Let's say I think in my simulation study I used 3 months. But that doesn't really matter. Let's say we follow every user who click on that for maximum of 3 months. If they converted during that time, we call that user a converted user or a converted click. But if they didn't, then we say that user, or we assume, because we never can know, right? We assume that user is not going to convert ever, never in future. So basically, we call that user an unconverted click or an unconverted user. So the user A in this plot is an unconverted click. So let's say like we waited enough and then we didn't see anything, any action coming from that user. So we call that an unconverted click or an unconverted user. User B converted. So we waited for, let's say, for a period of time, let's say 1 or 2 months, and then we got the conversion. He took the action, and then so we have the conversion result for him. But users C and D, those are kind of like the problematic ones. They click on the ad, but they have not converted yet, and then they have like we didn't have enough time. We haven't waited enough time to see if they are not going to, or basically to kind of be able to assume they are not going to convert either. So they are kind of like in the dilemma in between. They are going to convert or not. All right, so that's the kind of like a picture of the whole different types of user we may get. All right, this is some notation. I'm gonna skip. What time is it? I'm a little worried about the time. Damn it. All right, so maybe I should just skip. This is the notation I use, but because I kind of like cut off a couple of the slides, the ones that are kind of like more, it contains like more theory and then more symbols. So I dropped those, and then now this would not be super helpful. But basically, we get 1 sec. So Y is basically the conversion status that we can observe. C is the eventual conversion status of every click. So basically the true status, the true conversion status of clicks. D is the conversion delay between click and then conversion. A is just the age of click, and then X is just all the features that we have available in our data set. And then what we are looking for is just probability of C equals to 1 given X, all the features that we have. But again, we're not going to use that notations so much during this talk, unless I got some question that I need to go deeper. All right, so let's see what are the existing solutions for this problem. So then, like Sheffield in 2014, he proposed 2 approaches. The first one is not really his proposal, because the naive estimator, that is basically the logistic regression. I said it in the first place. Now, so everybody knows that. That's not something interesting. And we already know that is not a good solution. So basically, yes, whatever we observed so far, that's the eventual status of the clicks, or the conversion, the eventual conversion status of the clicks. And then we assume those are eventuals, those are the true ones, and then we treat them as the true conversion status, and then try to estimate probability of conversion based on those. Basically, that ignores all the conversion delay in between the click and then conversion. It would be super simple, super fast, but definitely it's going to underestimate the conversion rate because we know some of these unconverted clicks are going to convert. We just need to wait a little bit longer, right? So that's solution number one, which is the kind of just name estimator. The second one is the one that actually Schiphol proposed, and then he called it delay feedback model, DFM. So how it works is, sorry. So how it works is basically he, instead of using one GLM model, like logistic regression model, he used two GLMs. One was logistic regression model, which is related to the conversion status of the clicks. And then the second component was an exponential regression model, another GLM. And then that second component was for the delay time. I will talk about that shortly in a minute. I think in the next two slides, I will talk about DFM more with more details. This problem is not the likelihood or the objective function based on this approach is not convex. So it will get some convergence issues. And then also in terms of like computational, it's a lot more expensive. So it would be hardly scalable to a big data. And then how it works is just basically trying to simultaneously optimize all like the objective function with respect to all the parameters. So you can imagine how difficult they could get. Okay, so let's talk about DFM a little bit more. So how it works is say, okay, so at time t, if y of t, remember y was the observed conversion status of a click. So if y of t was 1, that means the click already has converted. So definitely c is 1. So because they like once they converted, they can't go back. They can just undo it. So C is definitely 1. That's just no question. There's no question. Everything is clear. We observe everything. But if y of t was 0, so that means the click has not converted yet at time t. So there are two possible outcomes here. C equals 1. So that means this click is not going to convert no matter how long we wait, or we just haven't waited enough yet. So basically A of t, or the age of the click at time t, is less than D. The delay time that we need to wait till we see the conversion, right? So there are two possible outcomes, and then exactly because we got two possible outcomes here, that's where the non-convexity comes in, and then makes the objective function a little bit ugly, and then makes our life like a lot harder to work with. So as I said it before, it's just basically a mixture of two GLMs, a logistic regression model and an exponential regression model. It's a survival problem because we need to wait till see that event. So of course that's obvious. But because we assume some of the clicks are not going to convert if we wait, let's say, for 3 months, then we call those clicks, those subjects, cured. So basically, they're not going to experience that event. They're not going to convert no matter how long we wait. So those are basically unconverted clicks. So that's basically a cure rate survival problem. So that's basically DFM. So I think everyone, at least everyone who is familiar with survival analysis, they are familiar with cure rate model. So that's a cure rate model. That's the DFM. I talk about that. I'm going to just skip that. So that's basically just putting those symbols and the notation into probability. So basically the logistic regression is probability of C equals 1 given X, and then the second part is F of T. That's a continuous distribution. So we better not to use P anymore. So F of T given X and C equals 1. So that's a kind of like interesting point here. We define D only for the ones who converted. So that's why we have an extra element in the given part, in the condition part. I think a couple of times so far I said I'm not going to talk about this slide and I'm going to skip it, but I still talk about it. I don't know why I even say that, but you know, I mean, it's hard to skip when you have something right in front of your face. Okay, so now I'm actually skipping that. So those are the ones that are already in the literature. If you go and look for it, you'll find it. What was our idea? So we had another idea. We said, we know like when we talk about display advertising, we talk about like tons of clicks in every minute. So that's a huge problem. That's a very huge data set that we get in every minute, in every day. And then you can imagine like how much like changes may happen over time. So we need to be quick. And then we need to be able to do it with a huge data set, with a big data set. So it's a big data, and then we need to be quick because things are changing pretty fast. So we said, okay, so now let's keep the question simple, and then let's look at the question from a different angle. So DFM was great because they Sheppel tried to kind of like basically use all the information that he got available, that means the delay time information, and then use that to kind of like estimate conversion probability in a better way, in a more accurate way. What was our idea? Our idea was, okay, so let's still use logistic regression. We know that's not a good solution. We know that's a misspecified model, and then we know that is a naive estimator. We know all of that. We know that we are going to underestimate the true conversion probability. We know that. But we also know that we can adjust. When we have, like instead, when we have a biased estimator, we know there are ways that we can kind of like adjust the estimator for its bias. So we said, okay, so let's do that. So how we can do that? One of those ways to do this is like using CLIC. And then that's basically Kullback-Leibler information criteria. So we used that information criterion to adjust the naive estimator for the conversion probability for its bias. We know it's underestimating it, but we'll find a way to kind of like adjust for it. I'll talk about that in a minute. So based on this bias adjustment, which is based on the delay distribution, of course, you probably already guessed that, and then from there we can basically adjust for the bias, and then get a kind of like more accurate and hopefully unbiased estimator for the conversion probability. So this is just basically a flashback to White's work in 1982. So he had a very nice theorem in his paper, and then he said, given mild condition, the conditions are really mild. You can just go and then look into it. If you just have a look to the paper, you'll see them. But under mild conditions, theta n star hat would convert to theta star almost surely when n goes to infinity. So what are those parameters there? What is theta n star hat? Is just the MLE based on the misspecified model. So we have a misspecified model, and then we got MLE out of that. And then what is theta star? Theta star is the minimizer of the click. That's called like Leibler information criterion. So like what it means is, so we have a true model, or the one that we assume is the true model, and then we got a misspecified model. By using CLIC, we can find the difference between these two models. And then what we can say is, okay, so it's easy to get MLE from a specified model because it's a simple model. It's just simply a logistic regression model. And then we know that like that estimator would converge to the minimizer of the information, the CLIC. The CLIC is just basically the distance between the likelihood or the log of likelihood of those two models. Basically, if we minimize, like if the theta star is an estimator who kind of like theta star is it's not an estimator, it's just a parameter. Theta star is just a parameter that minimizes, or we can actually say, sorry, yeah, it's actually an estimator, sorry. So theta star is just the estimator that minimizes the difference between the two models, misspecified model and the true model. Let me put it in a different way. Theta star is the best that we can get out of that misspecified model. We can't get any closer to the true model by using that misspecified model. If you want to go further, you need to change your model. You need to use another misspecified model, maybe a better version of it. So that's the main idea. So by using White's theorem, we can say that we can claim this is the best that we can get. All right. So how it works? We get theta hat here is just basically the conversion probability based on the naive estimator from the logistic regression model. And then if we use CLIC, we'll see P, like in the first line, P is just basically the minimizer of the click. So by solving that equation, we can find p hat, which is the conversion probability based on the MLE of the misspecified model. And then what is h? We got an extra stuff in extra item in that equation. H is just basically the distribution function of the delay time for the converted clicks, of course. This is when we have no covariates. That's why you see like everything is just so nice and then easy to work with. Of course, if we add more covariates into this one, it would get like kind of more complicated, but it's still there are ways to manage that. I'm not going to show that to you. I just showed this one to you just to kind of give you how the formula looks like and then how we do it. By looking at this formula, I wish I could kind of like annotate on this, but can you see my cursor, my mouse cursor here or no?
Yes, Abdullah.
Can you see where I'm? Yeah. Okay, cool.
Yeah,
cool.
Yeah.
This is good. So okay, so excellent. So theta hat is the MLE of logistic regression. We know we are underestimating by using this, and then like the at the bottom you see like the average of some distribution functions, because those are like the values, some quantities between 0 and 1. So the whole ratio at the bottom is actually a value less than 1. And then once we divide theta hat by that quantity, we actually kind of like bump it up, and then we get something closer. We kind of like increase that the value of theta hat, and then we get closer to the true value. So you see that the intuition behind this. And then of course the longer delay we get, we need to kind of like the multiplier needs to be bigger and bigger, so you can see that from that equation. So what about h? So now let's talk about this. I talked about this one so far. So okay. So back to here. So it's easy to get an estimate for theta hat, because all we need is just the binary outcome, like convergence, observed convergence status, and then a bunch of like features that we have. So we can easily get theta hat from a logistic regression model. But what about h? We said h is basically for the delay part, right? So what about that? So that's another classic problem, right? So we can use, like, you can simply use another GLM, that's the exponential survival model, and or exponential regression model. But because we have sensor data, we need to make it a kind of exponential survival model to estimate the parameters in that exponential distribution. So that seems simple. That seems like a straightforward. But the problem is censoring rate is really big at the beginning, especially at the beginning. So MLE of that model, that survival model, is going to be biased. So we know, like, whatever we know about MLE, all the nice features that we know for MLE, they are all asymptotic. So that means for a small sample size, there is no guarantee that we are actually estimating something good, or we are like any close to the actual quantity, to the actual parameter. And then we say sample size. What we really mean is like sample size of the complete observation, complete cases, not the censored one. So because we have a very huge censoring rate at the beginning when we're following a campaign or a user. So the MLE would be biased. So again, we need to kind of like adjust the MLE of the delay distribution for its bias. And then this time we used Fair's approach in 1993. So in that case, like basically he suggested, he proposed an approach to kind of like adjust MLE for its bias, especially when the sample size is small. And then you see like how it works. It basically works with the penalized likelihood function. If you see like L star of theta is equal to L of theta, which is the usual likelihood function, times a penalty term, and then that penalty term is just basically the Jeffreys prior for theta. So that's the penalty term that first proposed. So we use the same penalized penalized GLM, I would say. Yeah, penalized likelihood for a GLM to estimate the parameters for the delay distribution. So that was the second adjustment we made. After doing all of that, so what we get at the end is Okay, so it seems I'm just look at the time. It's 7:12. I'll try to be a little faster and then kind of like cut the extra. Okay, so we end up to have like 4 estimators. I already talked about naive estimator and then DFM estimator. So I also like define Oracle estimator. Oracle estimator is not a realistic estimator because in that estimator we assumed we already know the eventual conversion status of every single click. And then we estimate the conversion probability based on that. Of course, we don't know it in the real in a real scenario. That's basically the gold standard, and then we wanted to know how close we can get to that estimator. But definitely that's not realistic. We're comparing. That's just basically the bar that we can. This is where as far as we can get. And then the adjusted estimator is the one that we proposed. I like to kind of call that click because it's related to click. We are talking about clicks, and then also related to the callback level information criterion. So I actually wish I called that click, but I didn't. That's sad. Okay, so this is the plot basically. So what you see here is you see like on the y-axis, you see the average bias of the conversion probability, and then on the x-axis you see like from the day 1, day 0, time 0 is basically when those users click, and then what you see on the x-axis is basically how many days we followed those clicks to see whether they will convert or not. So as you can see, this is based on a simulation study. So that you see we tracked the clicks we followed the click for only 2 months, not 3 months. At the very top, the red line is just from Oracle Estimator. So you see that's just not even biased. And then that makes sense. We got a huge sample size, and that's based on the eventual conversion status. So there is no reason to be biased. So the bias is always 0, or the average of bias is always 0. And then at the very bottom, the purple line is from naive estimator, logistic regression estimator. Of course, that's underestimating, and then you see a hugely underestimating, and then you see. By the way, all of these estimators will converge to the true probability of conversion, but it's just a matter of time. The question is how long we need to wait. Even that naive estimator will converge eventually to the true conversion probability. But as you can see, even after 2 months, it still has a long way to go. Like we are underestimating like about like 4% or more maybe. A little bit more than 4%, and then 4% for conversion probabilities when you see like the after 2 months is huge, and then the other two in between, the blue one and then the green one, those are from DFM and then the adjusted estimator respectively. So you see DFM, like the adjusted estimator that we proposed, is actually performing better than the DFM estimator. Something I need to add to this part is DFM is not the MLE in here in this simulation scenario, because this is based on a simulation study, right? We know what was the true delay distribution, and then we also know what was the true probability of conversion. So the true delay distribution was a viable distribution, but the distribution that we assumed for delay time for both approaches, like DFM and then the adjusted estimator, in both cases we assumed an exponential distribution for the delay time. So basically we assumed a misspecified model. So none of them is MLE in here. And then you see under a misspecified model, our estimator outperforms DFM. And then the reason we didn't assume a viable distribution for the delay time was you remember earlier I mentioned like the likelihood function or the objective function of DFM is not convex, and then we got to a huge convergence issue when we assumed an exponent and a viable distribution for the delay time. So kind of we're forced to use a simpler model like exponential model, and then Sheffield in his paper he only used exponential distribution, no other alternative. And then exponential has its own limits, right? It's actually pretty limited. And then you see, so under misspecified model, our approach or our estimator outperforms DFM. And then I said we need to be quick, we need to be fast too. Time is another very crucial element component here that we need to kind of like take into our calculation. So the naive estimator is the fastest estimator ever. No surprise, that's just a logistic regression. Of course, it's fast. So for this small sample size that we used, it only it only takes to run for about like less than a second, basically, because that's just 9% of a second. And then you see the standard deviation or sample standard deviation is pretty small too. For our adjusted estimator, it took us like about like a little bit more than 5 seconds, and then for the DFM it took it like about 25 seconds. You see, like at the very bottom, I said like our approach was like 6 times faster for this sample size, and then for the time that we waited, like about like 2 months or 60 days, it's like about 5 times faster, not 6 times. But if we choose like a bigger sample size, or if we track the clicks for a longer period of time, you'll see like you're actually going to be even more than 6 times faster. So it really depends on the sample size, and then also depends on the how long we want to like follow the clicks, and then to see whether we see a conversion for them or not. Okay, all right. So that was like basically the result that I wanted to show you from our simulation study. So let's talk about the kind of like takeaways. So I didn't show you the results from a true specified model. But we did that, and then we realized our adjusted estimator and the MLE in this case would be DFM, they actually performs pretty similar. So we don't lose anything compared to the MLE if we use our bias adjustment approach. So that's when everything is all right, and then we know the true model. But under misspecified model, the one that I showed you the plot, our model actually outperforms that's not MLE anymore, the DFM estimator. And then of course, naive estimator was not in the discussion because it was just looked very off. And then our bias adjusted estimator was always faster, computationally a lot faster, and then more efficient than the DFM. And then the difference between the two, as I said it before, really depends on the sample size that we have. And then as we get like bigger sample size, which is the case in the streaming data set, because clicks are coming in every second. So the difference between the two estimators would be larger and larger. So the future work, which is still ongoing, is something that I didn't discuss here is like the users can click on the ad multiple times. So that means, let's say I look for something today, and then I did it again tomorrow, and then I did it next week, and then so that means I look for that item 3 times in a period of like, let's say a week, and in every time I actually clicked on the ad, and then I visited advertiser's website. So now, like in my history, in my click history, there are 3 clicks. So what I discussed it here, we basically considered only the very last visit, the very last click, and we ignored anything else before that. So that's not really using all the information that was available for me, for this user, right? So the question is, what about that scenario? What about if we want to use all the information, all the visit history for every single user, and then try to estimate conversion probability? The question remains the same. We just have more information, and then we want to be able to use that. So that's question number 1. Question number 2 is, sometimes like a user goes or basically will be directed to the advertiser's website from different sources. One might be from Google, the Google search page or Google search engine, and then the other one might be from YouTube, let's say. The other time would be from somewhere else, from an application, mobile application, from a video games or whatever. So as you see, like the visits and then the clicks might come from different sources. So now the question is, so let's say at the very end, as a user, I converted, and then Google will be able to charge me for that conversion. But now the question is, so let's say Google charged me, not me as a user, but me as an advertiser. So charge me, let's say $100, And then now the question is, out of this $100, how we can basically allocate this $100 to different sources based on my visit history? That's another question. Right now, maybe the simplest approach is just basically looking at the last impression again, but that's not fair. So now what would be the better approach to do it? So that's another thing. So those are basically the main two future work. There are already solutions out there. You can just go and look for it if you got interested, but that's something we want to use our similar approach, bias adjustment approach, to kind of tackle those questions. And then here is just a couple of like main references that we use for this work. I already talked about it during my talk, but here listed. If you got interested, you can go and then have a look. But other than that, I think I'm done, and then I have nothing more to talk about. If you have a question, I would be more happy to answer that. Nobody asked me any question during this talk, and then that was the kind of like, I don't know if it was sad or it was the kind of like a good news. I don't know that.
Thank you, Abdullah. Thank you for your presentation. So it was very interesting topic. So I think the main reason people didn't ask because we were talking very interesting, and then we didn't want to interrupt you. So we left the questions for the very end. No, so I think we have we have 5-7 minutes. So our first question is from Professor John Hines. So he's here, so he wants to ask a question.
Hi, thanks very much for the talk. So it was very interesting to see the performance of the bias adjustments. But in your simulation, you were taking a Weibull distribution for the delay times. What happens in a situation where you have much more where you have a lot of heterogeneity in the users? So you don't really have one. I can think of sort of users who are likely to be quick, short delay times, and others much longer. How do things perform in?
Very good question. That's a very good question, and then I may not have a good answer for that question. But there was more things to talk about, and I didn't because of like the lack of time that we had. So in the real scenario, we actually have different campaigns. So that means based on the company and then based on the products that like the different companies, different advertisers they have, there are different campaigns. So basically, we can propose the same model for every single campaign. So if we do it that way, then there would be a lot less heterogeneity, or like a lot less variation from one click to another click. So that's one way to do it. And then another thing that we proposed, but we actually never worked on it, was let's use because we have tons of different campaigns, right? It may not be really efficient to kind of like you have one estimator for every single campaign. It doesn't seem feasible, right? So what we proposed, but again, we did not work on it, or we have not worked on it yet. So we said, what about like treating that campaign ID, which means mainly different companies, as a kind of like a random effect, and then try to kind of estimate that variation or that heterogeneity across different campaigns from that by a lot less number of parameters. So that was another solution. But again, that was just an idea, and then we didn't go anything further, or not yet.
Okay,
but so that's a very good question, very important question.
I think that relates back to something I thought early on, that if you had sufficiently rich data, you may be able to essentially go backwards from conversions to clicks to work up to get some idea of delay times. But my guess is the data doesn't usually come in that form.
The data. Okay, so that's a good question. We don't have sample sets issue, but the issue is if we go back old enough to get enough sample, then those are like the old data. They're not really helpful. Yeah. They're not really useful, because if we talk about like clicks like a year ago, that's not going to really help us to get to kind of like good estimator now today, right? So yes, then yeah, I give it that.
Okay, thank you, John. Maybe we have time for another question if anyone wants to ask. Okay.
Dawood, I'll have another quick question.
Yeah.
So in bias adjustment ideas, something that comes to mind quite often are bootstrap type techniques. Has anybody given any thought to the role, the potential that you?
No, I have to say no.
Okay.
I would be more than happy if you have an idea and then talk about it. But I myself, I have not.
Okay. Thank you, John, and thank you, Abdullah. So I have plenty of questions, but maybe I can ask you in private. But one of my main questions was, do you have or have you considered to, because at the earlier beginning of your talk, you were saying that you follow up, for example, people for a specific period of time, like 2 months, 3 months, or so. Is there any optimal follow-up time that is gonna follow up, for example, a person to maybe finally they will do some action on the advertisement? For example, is 2 months enough or 5 months or more?
Yeah, okay, so that's another good point. This is another question. I don't know that. So what we like basically the 2 and the 3 months that we basically used in our study and then in our analysis, it was just basically from the expert in the area. So we talk with marketing expert, and then they said, okay, so if like somebody didn't basically convert, they also look at the history, right? They could see what was the maximum, or what was the distribution of the delay time for the ones like that converted like in the past, and then they come up with that 3 or 2 months. But we did not really actually look at that as another factor to see, okay, so what would be the effect of that on our like let's say result, the final result. No, we did not do that. But that's another thing. That's another interesting point. Yeah.
And one final question. Maybe I'm not expert and I don't know much about these things, but is the model working online? So I mean, so how often the model will be updated based on the data you have? Do you run a model once and then use it forever, or is it every week, every day, every second?
No. It really depends. It depends on the campaign. It depends on the campaign, how much you get for that campaign, basically how often do you get clicks for that campaign, how often do you get a new product for that campaign, how many different ads you got for that campaign, and then how much that campaign is willing to pay you, right? They're all different factors that would affect. So there is no unique answer for every single ad, no. But it really depends on that, and it also depends on that. It depends on, like, let's say if that's Google, they have like tons of like computation resources, right? So they can run this model more often. They actually have an algorithm how to efficiently update the model. So there are different ways to it. It doesn't have to be rerunning the entire model. There are ways to kind of update the model, but again, that depends on what, like, who we are talking about.
Okay, thank you. Thanks, Abdullah, for your presentation and all people who joined. So I may end the session now. So thank you all for joining. So thank you. Hope to see you in our next webinar. Thank you. Bye.
Thank you, Abdullah. Bye.
Thank you.